Recording is rolling. It is Thursday, November 21st. All right, so here's top scientists for that in-class quiz that guys took yesterday. All right, so this one here. All right, now I gave you guys a new grid page. All right, you guys write your name on this. All right, so here's the deal with this. Is actually when I gave this quiz, was kind of expecting for grades to be really good. Students gonna brace me this. If I have any problems, probably they're gonna have like 20, 30 minutes to go. So I better set out some books for them to read if they have spare time. And the average grade is gonna be like a 90. And well, it didn't quite pan out like that. Now, if you're on this list of top scientists, you did pretty good. Right, so got some names here. But overall, students struggled with this a lot. Right, so my plan then, like at the end of the day yesterday, is like, okay, well, that's okay, because what we'll do is I'll just wait for all of the students to make up their quizzes. They have to make it up, and then when I get them all in, then I can go over the solutions and have students do corrections, and that would be good. That would be good, except, well, here's maybe kind of an indication. The quiz before that was energy quiz, this take-home quiz. I'm still waiting on a bunch of these. Like about a fifth of all my students have not even turned that one in yet. And kind of similar proportion yesterday. About 1 in 5 students never even took this. I had reasons all day yesterday why, oh, I can't take it because I can't take it. So it's like by the time all the students get around to taking this, it's going to be Christmas and time's going to run out. So I can't really do that. So that's not going to work either. Right. So here's a solution I came up with. Is we're going to have a redo. We're going to have a fresh redo. So I'm going to walk you guys through this right here. If you made this top scientist list, then that's going to translate into a +5 bonus points on this new grade. But I'm going to throw out the scores from yesterday. We're going to walk through this and do this today. And today's score will be the score on the in-class quiz. How's happening? And if you did really well to start with, you get a bonus. So it'll be all good. All right, so, all right, you guys ready to go? All right, number 1. Oh, yeah. I would just focus on the one today. Yeah, we're doing today. Yeah.
Is there a version A?
Huh?
Is there a version A?
All right. Yeah. Tell you what, we're gonna throw out the ones yesterday. Let's not even worry about those. We're all gonna do this one today. Okay. So we're all doing this one. That's what we're doing. All right. So first question. 2 forces applied to a 2 kilogram block on a frictionless horizontal surface shown in the diagram. What is the acceleration of the block? What's the acceleration of the block? Guys, if you have forces and a mass, we're talking about Newton's second law of motion, right? So the acceleration, that's what you're trying to solve for, right? Just net force divided by mass. Okay, so let's step through this. Guys, what is the net force on that block? Right, A to the left, 3 to the right. Are those going to subtract from each other because they're opposite directions? Right? You guys figure out the net force? Right, so there's your net force, right? And is it a net force to the right or to the left? Yeah, because that's where more force is going. Wherever there's more force, that'd be the direction of the net force, right? Right? And then divide out the mass of the block, that'll give you the acceleration. And it should be one of those answer choices right there. Right? Do you guys see the correct answer choice? Right? And the direction, of course. Right. All right, you guys good? Right, number 2, graph shows force versus acceleration for some mass of an object. What is the mass? What's the inertial mass? Oh, guys, force versus acceleration. Right? That sounds like a graph version of Newton's second law of motion all over again. That's just this right here. F equals ma. Is that kind of like y equals mx? Y equals mx. Right? Here's your y-axis, force. Here's your x-axis, the accelerations. Right? So what property of that graph tells you the mass? Not the area, the slope. Aha, the slope. Okay. Can you guys do your rise over run, the slope? As if you're walking uphill. How steep is that hill? What's rise over run? Okay. Because that would be, say, newtons divided by meter per second squared. That would give you a mass in kilograms. Right? Can you guys do that? Right. Right. Number 3. What is the base SI unit for mass? Mass is measured in, right there. Look at that. You guys know how to measure mass? Yeah. Yeah. Yeah, it looks like rise over run. Like So go back to number 2. This graph follows this formula. It's the same thing, right? So your y-axis is like your force. Your x-axis is like your acceleration. The slope is like this mass right here. So you do rise over run. So it looks like going from 0 to 0 to, well, to get to 3 meters per second squared required 1.5 newtons. So the rise is 1.5 newtons. The run is 3 meters per second squared. So there's 1.5 newtons. There's 3 meters per second squared. Can you divide that over and solve for the mass? Right? As in rise over run. All right. You guys know how to measure mass? That's number 3. Number 4, 2 cars with different weights. I'll pause right there for a moment. Guys, if 2 cars have different weights, is it pretty safe to say they also have different masses? Okay, so maybe that could help a little bit. Right, let's see. Are traveling on a level surface at different constant velocities. Right. So now we got 2 variables we're juggling, right? The mass or the weight, right? And also like velocity. So we're juggling different variables, right? Within the same distances, greater force will always be required to stop the car that has the greater width. Right. So I'll show you guys 2 different ways to approach this. Right? This one's a little bit more involved than most of these questions. Right? So one way is you could do a comparison in your mind. Say, okay, what if I have these 2 cars? Okay? They could possibly be different masses, but maybe the masses are similar. Maybe it's like 900 kilograms versus 901 kilograms. Or maybe it's crazy different. Maybe you have like 1 kilogram toy car zoop, versus like an SUV. Go away. Maybe it's like, great. And what about speed? Same story. Maybe it's like 20 versus 21 meters per second. Almost the same. Or maybe one's going at like 1 meter per second and one's going at like 100 miles an hour. Right? Okay. So you got any combinations of those things. Right. So what's going to be the greater force to stop? Right. So if you could think of a counter example, then that's probably not the answer. Right. So for example, weight, the one with more weight. Does the one with more weight always require more force? Well, what if they're kind of similar in weight and the smaller one is just going super fast? Zoo, zoo, zoo. If you're standing in front of these cars, which one do you want to stop? I might pick the heavier one if it's going way slower. This guy's going like 1 mile an hour. Slow me down. It's your point. Right? So it's probably not weight or mass for that matter. Acceleration, that's just the rate that it could be speeding up or slowing down. It's like a kinematic thing. I don't think that's going to help. Velocity, well, all else equal, I would say the faster car would be more difficult to stop. But that's not necessarily true if the weights are crazy different. Guys, what if you have a little tiny toy car zipping at you? Like 20 meters per second. It takes some force to stop that. Versus an SUV, like, here I come at 19 meters per second. Do you want this SUV barreling at you, even though it's going a little bit slower? Ooh, definitely not. Okay, so that's why it cannot be that answer either. Right? Because look at kinetic energy. Hey, that involves both mass and velocity, but both mass and speed. Okay, so now we're considering both options. In fact, the answer is on this poster. This is the answer right here. So you have different cars, different mass, different speeds, right? They could give them different kinetic energies, 1/2 mv squared, right? Now the question is, which requires more force to stop it given the same braking distance or the same stopping distance? Maybe if they stop it like 10 meters or something. Okay. So hey, could you just take this force distance and slide it over here, add it over? And if it's the same distance, like 10 meters, whatever, 1 meter, right? As long as it's the same for both. Hey, whoever has the greatest this going on would therefore require the greatest force to stop it. Guess that? The answer's right here. Right? Guess that? All right. Ready for number 5. In the diagram below, 20 Newton force pushing a 2 kilogram cart for 5 meters. What is the work done on the cart? Work. Guys, what's the formula for work? Boom. Force times distance. It's all in the same direction. There's your force. There's your distance. Boom, boom. Can you guys calculate how many joules of work? Force times distance. Number 6. Got some unbalanced forces applied to 2 blocks. Block A and block B. The graph below shows relationship between force and acceleration for block A, force versus acceleration for block B. Compared to the mass of block A, the mass of block B is, okay. Hey, that's the graph that you guys saw earlier today. Does that look like just Newton's second law of motion turned into a graph? X-axis, y-axis, and the slope tells you the mass. Right? The slope would be the mass. Right? So let's compare the slopes of these 2 graphs because that tells you the mass of each block. Right? So Guys, who can tell me what is the mass of block A? Right? Does everybody see that? Right. 3/3, that's like 1 kilogram. What's the mass of block B? Ooh, guys see a rise over run of like up to over 1, right? Newtons, meters per second squared. Guys see how many kilograms is block B? Got twice the slope. Gonna be like twice the mass. Right? Guys get that? Number 7, 50 Newton horizontal force needed to keep an object weighing 500 Newtons, moving at constant velocity. Boom. Guys, when you see constant velocity, what do you know about the net force? What's the net force equal to? Zero net force. Okay, we're going across a horizontal surface. What's the magnitude of the friction force required? Okay, here's exactly what I'm thinking. Right, is this right here. So they just told you the applied force, and they told you constant velocity, which means all the forces zero out. Okay, so these two vertical zero out, whatever. Right? But these two horizontal forces zero out. Okay, so if you're pulling with some force, and you want the net force to be zero, then what does the friction force have to be equal to? However much you're pulling with, right? And if you're pulling with however many newtons, I bet the friction force is that same number of newtons, just the opposite way to zero out the net force, right? True? All right. All right, you guys go through number 7? Okay, number 8. A different force is applied to each of these blocks. Okay, let's look at the blocks real fast. So they're all 1 kilogram. Right, so all the same mass, all the same weight. Right. So back to the premise here. Slide across a steel surface at constant speed. Again, constant speed, you know the forces zero out. So if I needed a free body diagram, I bet it would be exactly that all over again, wouldn't it? Same free body diagram as before. Okay. All right. Which diagram is the coefficient of friction the smallest? Coefficient of friction. Is that this green box right here? That's the ratio of 2 forces. Which 2 forces? Friction over normal. Right? Okay, so if I had the friction force and the normal force, I could answer the question. Right? Right. Now, let's start with the normal force, because I think that one's easy to check off. Guys, what is the normal force acting on every one of those blocks? Huh? What's force measured in? Newtons? Right. Here's a different question. How much does each block weigh? 10 newtons. Doesn't 1 kilogram weigh 10 newtons? Right? Because that's what this is right here. That's what mg is. 1 kilogram times 10 meters per second squared gives you 10 newtons of weight. Well, guys, if it's 10 newtons of weight, what's this normal force right here? 10 newtons. Isn't that the same for all the blocks? Right? Okay, so they'll have the same 10 newtons here. Right? So that's the same. It's all the same 10 newtons. Right? So the smallest coefficient of friction, therefore, would correspond to the smallest friction force. Isn't that true? Right? And the smallest friction force, well, I know the friction force has to match the applied force because constant velocity. True? Right? You guys get it? So let's see. So whichever one you're pushing with the smallest force to keep it at constant velocity, that would also be the smallest friction force, which, because all the blocks are the same mass, would correspond to the smallest coefficient of friction. Right? Right, you guys get that? Right. Any questions so far? That's good. That's good. All right. Number 9. Diagram below. A box on a frictionless horizontal surface. So maybe an air hockey table. We got forces F1 and F2. If force 1 is bigger than force 2. Hey, this looks a lot like question number 1, doesn't it? It's almost the same question. Right? So if you're pushing to the right more than you're pushing to the left, which direction is the net force? Okay. And therefore, guys, does a net force result in a constant velocity or a constant acceleration? Which one? It's right here. Right? Okay. So how much does something accelerate? Well, that's proportional to the net force, right? So if you have a net force, you're accelerating. True? Right, guys good? Guys ready for number 10? Which 2 graphs represent the motion of an object where the net force is 0? The net force is 0. I have an example right here. Right? Here's something moving on a horizontal surface with net force equal to 0. I know its net force is 0 because constant velocity. Okay, true. So I got some grass right here. Guys, you're driving on I-95 straight north towards Jacksonville. Just go, suppose your cruise control, 60 miles an hour, 60 miles an hour, 60 miles an hour. Your speedometer needle is not moving. It's always 60 miles an hour. That gives you a constant velocity. All right, so the velocity is constant and the constant velocity scenario. Right? The distance you accumulate increases at a constant rate. So in the first hour, you pick up 60 miles. The next hour, you pick up another 60 miles. The next hour, you pick up another 60 miles. That's called 60 miles per hour. Right? Do you guys see a pair of graphs that looks like that? Because if you do, that would describe the scenario. You guys can do that? The table below lists coefficients of friction for four materials sliding over steel, which is the lowest friction force. All right, I think we're just back to this all over again. Okay, so they gave you, you do have to make a reasonable assumption for this one. Let's assume the blocks are the same mass and the same weight. Right, okay, so some of these you have to make little simplifying assumptions. Okay? Same mass, same weight. Let's call it the same normal force, therefore. Okay? Now, if you're looking for the lowest friction force, guys, the lowest friction force, that would correspond to the smallest coefficient of kinetic friction, I think. All right. Do you guys see an answer that stands out then? Okay, you guys good? 12. What is an essential characteristic of an object in equilibrium? Ooh, guys, equilibrium. If something's in equilibrium, what is the net force equal to? 0 newtons. Therefore, what is the acceleration equal to? 0 meters per second squared. Right? Could the object possibly be at rest? Yeah, it might be at rest. Could it possibly be moving? Yes, but if it is moving, it's moving how? Constant velocity. Yeah, so that could also be equilibrium. Yeah, equilibrium, 0 net force, 0 acceleration. And it might be at rest or it might be constant velocity. 13, which is a vector quantity. So in this class, we have vector quantities versus scalar quantities. Guys, what does a vector have that a scalar does not? A direction. So a scalar is just a magnitude, like how big, a number you can punch in the calculator. A vector has a magnitude also, but also has a direction associated with it. Okay. So out of these options, which one has a direction? Well, let's go through all of them. Speed. Ooh, guys, there's speed and there's velocity. Which one has the direction? Speed or velocity? Velocity. I think speed is just a magnitude. It's just how fast are you going. If you're driving in your car, suppose you're going around a big old circular racetrack. Is your velocity changing? Yes, because your direction is changing, turning the steering wheel. Your speed might be constant. That's okay, right? Because your speedometer is the same number all the way around. Okay? Right, so speed is a scalar. Okay, guys good? It's kind of a similar story with distance. So let's go back to that circular racetrack. You drive all the way around the track. Did your odometer just add up the full distance that you went around? Yeah, sure did, right? Now you end up exactly where you started. So what is your displacement if you end up where you start? 0. So your distance is the circumference. Your displacement is 0. Displacement is the vector. Distance is the scalar. Okay. Power. You guys just learned about power. Power is work over time, like a rate transfer of energy. Does that have a spatial direction to it? Not really. Okay. Force. Hey, do you have to know the direction you're applying a force? Absolutely. Otherwise, you couldn't answer questions like number 9 at the top of the page. Right? So force has a magnitude, how much are you pushing, but also a direction. Are you pushing left? Are you pushing right? Okay. All right. So you guys got that? What's a vector? What's a scalar? 14. Diagram shows a granite block sliding at constant speed. Oh, right there, sliding at constant speed. So already, I forget what the question is, but already I'm thinking, what am I thinking? Aha. Right. I bet if you drew a free body diagram, it would be pretty much that right there. Here's the pushing applied force. Here's the friction, weight, normal force. Wouldn't it look just like that? Okay. So I'm thinking about this in my mind. Which pair of quantities could be used to determine the coefficient of friction between the granite and the surface? Here's your coefficient of friction right here. Right? Coefficient of friction is what compared to what? Friction force compared to normal force? Is that an option? Friction force compared to normal force? Is that an option? Right, guys good? At 15, object moving at constant speed, 25 meters per second, has 450 joules of kinetic energy. Kinetic energy. Okay, so here's a new formula. I meant to flash this up on the screen earlier today, but I don't know. Do you guys remember yesterday, all during class, I left this up all during class on the projection? Okay, so you have kinematic here, you have dynamic here. Here's energy and kinetic energy. Isn't that this one down here? Okay. This, by the way, I think it's all the formulas you really needed for this entire in-class quiz, right? But I've also got it right here, right? So kinetic energy, 1/2 mv squared, because this is the review that we did a few days back. Okay? So they just told you 450 joules. So say K equals 1/2 mv squared. So did you guys type in your calculator right now? 450 joules. You guys got that? So you type 450 for 450 joules. Right. Now we're solving for this mass right here. I want to know this mass. So I got to know the speed. V could be velocity speed. Right? And that was 25 meters per second. Right? So take your 450 joules, cross multiply this 2, divide by 25 squared. Okay. So I'll say it again. Take your 450 joules, cross multiply 2, then divide out this 25 squared, and that leaves you with mass. A little bit of algebra. Can you guys solve for mass? Okay. Or alternatively, you could start from the answer choices, go through them one by one, and run 1/2 mv squared until you get 450 joules. There's only one answer choice that would do that. Right? Does everybody have the answer? All right, number 16. Diagram shows a moving 5-kilogram cart at the foot of a hill that's 10 meters high. For the cart to reach the top of the hill, what's the minimum kinetic energy in the position shown? Okay. You guys remember that 3-page energy table had those 12 examples on it? Right. This looks a lot like those examples. Right. So what's the energy at point A? What's the energy at point B? And you can set up an equation. So what kind of energy at the bottom of the hill? Kinetic. Yeah, the car's in motion, but we'll call that height 0. So it's all kinetic. Suppose the cart rolls up the hill. Is it slowing down as it's rolling up the hill? Is it slowing down? Yeah. Not because of friction necessarily, but because of it's gaining height. It's Earth's gravity field's doing negative work on it, sort of thing. And then it gets to the top of the hill, and it's supposed to just barely gets to the top. It just comes to stop right as it barely gets to the top. Now it has all what type of energy? Potential. There's your MGH, right? Guys, is the kinetic down here 1/2 mv squared equal to the potential MGH up here? Yeah, yeah. I do have a poster that has the same equation set up on it, right? It's a little bit different story, but it's actually pretty similar in some ways. Okay? So energy at the bottom, 1/2 mv squared. Energy at the top, MGH. Okay? Now the question is, how much kinetic energy did it start with? But they never told you what did they never tell you? They never told you the speed. So you can't really use 1/2 mv squared. But you can say it's equal to MGH. Aha. And I bet you know M and G and H. You guys know the mass of the cart? Do you guys know gravity field? And probably a reasonable assumption is that we're on Earth, where carts are. And you guys know the height of the hill? You see M times G times H. Do you guys see an answer choice that says what your calculator screen says right now in joules? Because energy would be in joules. Right? Is that working out for everybody? All right. Yeah. Silent, yes. A net force of 25 newtons applied horizontally to a 10-kilogram block resting on a table. What is the magnitude of acceleration? Hey, that sounds like Newton's second law. So take the force, divide by the mass. Can you guys do that? Force over mass, that gives you acceleration. Boom, boom. You guys got Newton's second law of motion? All right, Newton's second law. If the sum of all the forces acting on a moving object is 0, if the net force is 0, the object will do what? Because if all forces sum to 0, the object is in a state of what starts with an E. Equilibrium, right? Now, if something's in equilibrium, I'm thinking more like Newton's first law, right? Could the object possibly be at rest? Yeah, it might be at rest. Right? And if it's not at rest, it could be moving. Moving how? Constant velocity. So that's with the same speed, but also in a straight line, constant direction. So it's not speeding up, it's not slowing down, It's not going around any curves because those would all be different types of acceleration. Linear acceleration, centripetal acceleration. Okay. But to accelerate, it would need some kind of net external force. If there's zero net force, there's zero acceleration. 19. A net force of 10 newtons accelerates an object at 5 meters per second squared. Now, pause right there. Let's do a quick calculation here. They just told you 10 newtons accelerates something at 5 meters per second squared. Can you guys real fast solve for the mass? Can you guys do that? Okay, 10 newtons causes an acceleration of 5 meters per second squared. All right, you guys got the mass in kilograms? Okay, you guys write that down real fast. Okay, so now everybody knows the mass in kilograms. Okay, so what net force would be required to accelerate the same object at 1 meter per second squared? So now I'll take the mass that you just found, multiply by 1 meter per second squared, and that gives you the force in newtons. Okay, you guys get that? You guys good? Newtons. All right, 20. Graph below shows the relationship between gravitational force and mass near the surface of near the surface of Earth. F equals. Hey, this is really similar to something you guys saw earlier. It's another graph version of Newton's second law, except they swapped what the axes are. So no, the y-axis is still the net force. That's okay. Okay. But guys, what they put on the x-axis? The mass is down here. So here's your y-axis is force. Here's your x-axis is mass. So what does the slope represent? Acceleration. And then it's just y equals mx all over again, right? So y equals slope times x, right? Now, one more little detail. It's a special kind of force. It's a gravitational force. That gives you a special kind of acceleration called gravitational acceleration. Spring scale reads 20 newtons as it pulls a 5 kilogram mass across the table. What is the magnitude of the force exerted by the mass back on the spring scale? Ooh, what law of motion does that sound like? The equal and opposite rule, exactly. Newton's third law. So if you ever have two interacting objects, in this case, maybe like a mass and a spring scale, maybe pushing or pulling on each other, they push or pull on each other with exactly equal and opposite forces. Right? So you guys got that? Equal and opposite rule right there. Newton's third law. 22. An object rolling across a level floor without any horizontal net force. As if you have zero net force, is that equilibrium? And if you're in equilibrium, what are you doing? Are you speeding up, slowing down, going around curves, or moving at constant velocity? Constant velocity, right? Okay. Like you guys remember Voyager spacecraft? This was launched back in the 1970s. Is it still moving to this day? Yep. How much force is required to keep it going? None. It's just going. It's just going. Just inertia. It's just going. Constant velocity. An object falling to Earth in the absence of air resistance. Ooh, guys, absence of air resistance. Is that called free fall? Is that this one right here? Free fall? Right. Now, if something's in free fall, is it falling at constant velocity or constant acceleration? Constant acceleration. And on Earth, that's about 9.8 meters per second squared. Yeah, you guys know the units for acceleration, right? Meters per second squared. Which of the following is not one of Newton's laws of motion? Oh, well, let's look at Newton's laws. So first law of inertia, object at rest, stay at rest, object in motion wants to maintain its velocity unless there's an external net force, something like that, law of inertia, right? Newton's second law, well, if there is a net force, it's going to cause an acceleration. So force is proportional to acceleration, mass is inversely proportional, so directly proportional, inversely proportional. More force, more acceleration, more mass, less acceleration. And then Newton's third law is the equal and opposite forces rule. Now this is, you have to have two interacting objects to make this happen. Equal and opposite forces, right? Right. Now your multiple choice answers, I think every statement is a correct statement within itself, but one of those is not one of Newton's laws. Do you guys see which one is not Newton's laws? and the other three are. Okay. All right. Oh, a ball is thrown straight up with a speed of 12 meters per second near the surface of Earth. There's no air drag. What is the maximum height? Ooh, maximum height. Fine. There you are. That's right here. Okay. Guys, this is a question that keeps coming up over and over and over this semester. So go back to kinematic days. You could have solved this way back in September with this right here. Third kinematic formula. Here's how high the ball goes based on how fast did you throw it. Right, just a little algebra rearrangement to get that. Right. Then, more recently, you guys learned a completely new way to solve it. Energy conservation. You throw it, it has all kinetic at the bottom, goes to the top, has all potential energy. You get the exact same height. Right? I think I've been asking that question about quizzes, right? It keeps coming back as a quiz question. You see it in class all the time. Okay. So there you go. There's exactly how you solve it. Well, two different ways. Okay? So they told you the throwing speed. Okay, so you guys are doing this in your calculator right now, of course. Right? Throwing speed squared divided by. Okay. And then 2 times Earth gravity. You can call it like 20, right, as a number. Right? If you want to plug this in your calculator, make sure you put this in parentheses down here, the 2g, if you do 2 times Earth gravity, so that it divides out correctly. All right, does everybody see how high the ball goes? Everybody's got that? Okay. Of course, more importantly, would you be able to solve this from scratch and be able to get this yourself? Okay, of course, right? Kind of showing you guys the answer here. How about you guys know a variation on this question? I like to ask proportion questions. So let's say we got 2 friends. I got how about Bill and Ted? Let's call them. And Bill could throw a ball exquisitely high, but Ted, he could throw it three times as fast. Excellent, guys! If you could throw a ball 3 times as fast, how many times higher can you throw that ball? 9 times. It's factor 3 squared. What is the approximate kinetic energy of 980 kilograms race car traveling at 90 meters per second? Well, where's my energy table? Here we go. Energy. So they said, what's the kinetic energy? They gave you the mass of the car in kilograms. They gave you the speed of the car in meters per second. Can you just run this expression right here? Kinetic energy, 1/2 mv squared. Right? The multiple choice answers are in scientific notation. So how about you might have to round the digits a little bit. Right? They did round correctly. I checked earlier. Right? Guys, what's 10 to the power of 6? Is that 1,000, a million, or a billion? What is 10 to the 6? 1 million. Aha. So if you saw 10 to the 6, that would be like a million. Okay. Okay. You guys good? Working it? What is an object launched into the air called? That's called a what? Projectile. All right. Get these. Projectile. 28. Approximately how far will an object fall in 3 seconds? Ooh, great. So whether you drop something from the edge of a cliff, or if you blast something straight horizontal, so it's like a projectile again, and it falls down, right? So one or the other, either dropping it or blasting it horizontal, right? So how far it falls, right? All right, here's a little kinematic days. Here's how far is a function of time. Here's how fast is a function of time. Here's how fast is a function of distance. So this sounds like a job for which equation? First, second, or third? First, yeah. How far is the function of time? Now, if you drop it, then isn't initial velocity just 0? Or if you blast it horizontal, initial vertical component velocity goes to 0. That goes away. Hey, look who it is. It's the college equation. You guys remember Paul Hewitt? It's an old mine shaft. Drop it goes, takes 5 seconds to hit the bottom. I wonder how deep it is. See, 5 squares, 25. It's about 125 meters deep. That's 5 squared times half of 10 is 5. It's about 125 meters deep. How'd you know that? College. You guys remember that? You guys remember college? Ooh, I got a whole table of values right here. Here's falls for 5 seconds. I wonder how deep it is. It's about 125 meters deep. College. This is right here. Right here. What's that? Okay. Now you guys got a little bit different question. You guys got 3 seconds of falling. I suppose you do. Show both at the same time here. 1/2 times 10 meters per second squared times 3 seconds being squared. See, 3 squared is 9 times 5. Right. Guys, how far will something fall in 3 seconds? And how'd you know that? College. That's right. College. What's the maximum possible height a pole vaulter would clear running at 6 meters per second. He's about to plant his ball. So he's running, and he plants his ball and shoo, goes up to, well, so maximum height. Guys, while he's running, what type of energy does he have? Kinetic. When he pulls straight, let's see, it goes straight up. He has what kind of energy at the top? Potential, right? Here's basically what's going on, right? Is this kinetic turns into this potential, like that, right? Remember, energy is a scalar, so the fact that he was running sideways doesn't matter. It gives you it's the same correct setup, right? So how high does he go? Well, the answer is also right here, right? So it's the same answer as the question from before, right? Notice his mass ended up canceling out. So the fact that they never gave you the mass of the pole vaulter does not matter because it cancels out right here, right? If you weren't sure about that, then you could make up any mass you wanted to. You could call them 50 kilograms, 60 kilograms, 70 kilograms. You'll still get the same correct answer regardless. Okay? Right. So what you guys do is running speed squared and divided by 2g. Right. And you guys got an answer choice? Right. Right. Again, if you plug this in your calculator exactly like this, make sure to put the 2g in parentheses so that your calculator knows to divide that all down there. All right, you guys got pole vaulter? Pole vaulter. A 60 kilogram skydiver is falling at constant speed. Ooh. I find falling at constant speed. Here we go. Right. Guys, already that we have a kind of a special scenario. If you're falling and you have constant speed, you have reached what kind of velocity? Terminal velocity. Isn't that exactly this going on right here? Okay. And your acceleration is equal to what? 0. Yeah. And the only way to have for that to happen is this guy falling through a vacuum or is he falling through air? Has to be falling through air, right? This would never happen in a vacuum because there would never be any this air drag. Okay, guys see that? Right. So guys good? All right, let's check this out. Skydiver. What is the approximate magnitude of force of air friction acting on the skydiver? Oh, well, if you have the free body diagram, the answer just pops right out of the page. Because isn't this drag force equal to what other force? Is weight. Hey. Did they tell you his weight in the premise? Or did they tell you his mass? Ooh. If you have his mass in kilograms, can you get his weight in newtons? Mass is in kilograms, weight is in newtons. Mass is M. Weight is mg. Can you guys get weight in newtons? And of course be equivalent to the friction force if he's at terminal velocity. A rock falls freely toward the ground from a given height. Air friction is ignored. Which statement is correct? All right, so we got a rock falling. Well, let's read them all. Let's see what kind of makes sense. Option A, the potential energy of the rock decreases as the rock moves closer to the ground. Ooh, guys, what's the formula for potential energy? mgh, right? So as the rock is falling, is its height decreasing? Therefore, is the potential energy decreasing? That one sounds pretty good. Let's check the other ones just to make sure. All right. Option B, the total mechanical energy increases? Wait a minute. You guys know something called conservation of energy? Can you create or destroy joules? No, so that's probably don't look too good. Option C, the kinetic energy decreases? Well, hold on a minute. Because if it's falling, is it probably speeding up? Yeah. If it's not speeding up, then maybe it's terminal velocity. But either way, the kinetic energy would not be decreasing because kinetic energy is 1/2 mv squared. So that's probably increasing also. In fact, it's coming from potential energy, right? Potential energy decreases, kinetic energy picks up, increase. Okay. D, the total mechanical energy decreases. No, because that would violate conservation of energy. So I don't like that one either. All right, so you guys see the correct answer on 31? Okay. 32, a 1/2 kilogram ball thrown vertically upward with initial kinetic energy of 25 joules. There's no air drag. How high will the ball rise? Okay, I'm going to break out this poster again because I think it's what we got going on. So they told you the initial kinetic energy. So that's just all this right here. Some number of joules. Right, you guys got how many joules that is? I think that's what I said, right? Yeah, joules. They told you the mass. And could you take a pretty good guess what the gravity field is? Okay. So take the energy in joules, divide out the mass, divide out the gravity field, and that leaves you with the height. Right? All right, that worked. All right, that good right there? All right, say it again here. All right, so they told you the initial kinetic energy. Right, so like down here, you throw it, it's all moving. Take that number. If you divide out the mass of the ball and divide out the gravity field, you'll be left with the maximum height. How high does the ball go? Okay. All right, guys good? Okay, so looking at this right here. All right, and last question. Last question says a rock thrown vertically upward reaches a maximum height of so many meters above Earth's surface. What is the rock's speed at its maximum height? Hey. You throw the ball straight up. How fast is it moving right at the very top? Aha. All right, so you guys got that answer too? All right, so double check, make sure your name's on your paper. All right, so before you walk out of class today, just have that quarter page in the gray tray, and I'm going to score those.